Good evening, everybody. Tonight's presenter is Dr. Mona Neary, Assistant Professor of the Energy Systems at WMG. She's going to be telling us about the role of modelling and software in the manufacture of batteries. Hopefully you've all read the synopsis, etc., so I won't bore you by reading it out again. May I hand straight over to Mona. Thank you very much.
Thank you. Thank you, John, for the introduction. And hello, everyone. Good morning, afternoon, or evening, depending on where you are. It's a real pleasure to be here presenting today. And thanks for John for inviting me. The talk today is about battery manufacturing control and the role of software and modeling in it. And this was initially the only aspect I was quite keen to cover, and then I realized battery performance measurement and management is also part of this story. So my slides are going to be on battery manufacturing and a little bit deeper dive, similar, the same level to the battery performance. So to start, I'll give a little bit of introduction about who I am and then who we are as WMG, and then a little bit of motivation around why everyone is talking about batteries, battery manufacturing, what are the challenges, and then a little bit focus on what we do actually, what is someone with a engineering role or a system prof or academic like myself is doing actually here. So who I am Mona Faraji, and I am originally from Iran, from a northeastern city in Iran. This area quite close to the sea, and also probably unlike many people's imagination, we have snow there. We have quite interesting like, let's say, natural spa around the area, and we have very beautiful historic architecture. So I moved from my city, which is called Ardabil, to Tehran around 2005 to start my education at Iran University of Science and Technology. And then after having my PhD around 2016, I had a career as a lecturer and a senior lecturer at another city in Iran. And then at 2018, I moved to UK for a new challenge. When I moved to WMG, I started taking the role as an, I'll go to that in a little bit later. Before that, to give you an introduction about WMG, WMG, or Warwick Manufacturing Group, we have been rebranded to just the acronym WMG recently, is a department of University of Warwick, and we are separate from our School of Engineering and also other like chemistry department, physics. We are a department for a standalone department of the university, and we are having that particular specification of trying to bridge the gap between the academia and industry, answering most of the industry related questions. WMG is having different research groups, different disciplines. We could like categorize them into 5. I am from energy. We used to call them directorate, and in energy directorate, we are very much focused on energy storage and energy systems generation, distribution a little bit, and batteries is a big part of it. In WMG, the battery group is about 50 people, and we are looking at different problems, starting from the material selection, synthesis, battery manufacturing techniques, battery manufacturing scale-up. Then we go to the battery system engineering, battery design, modeling, simulation, not only at the cell level, but also at the module and pack level. We do all sorts of tests, such as characterization, safety, and we also work around integrating battery systems inside different applications like electric vehicles, e-bikes, e-motorcycles, and also we're looking at the reuse and recycle to close that loop. We have quite good facilities, quite unique facilities as a university, and we have been in a collaboration with many industrial partners over the last 40 years. Beside everything that is quite related to the projects and industry, we have our own skills center that we are very much focused on upskilling the next generation, or educating the next generation of engineers and obviously academics, but also upskilling the current workforce in transition to an electrified future and electric transportation system future, and also net zero, that is quite popular terminology nowadays. So when I joined WMG, I joined as a research fellow, and I started working around battery management systems, modeling and control algorithms. And then I was promoted to a senior research fellow working around the modeling of powertrain systems for electric vehicles and e-motorcycles. And then I was promoted to an assistant professor. And the last 3 years, it's been mostly focused on battery manufacturing, modeling, optimization, and control. By background, I have always been a control engineer, and AI and artificial intelligence has been always a part of my my journey as a PhD, and then later as a researcher since about 2019, when I started my PhD. During this time, I have been working in WMG. I have been working with many big or small industrial partners and institutions, such as big UK Battery Industrialization Centre, or Faraday Institution, which is heavily funding the battery research in the UK. So, as I mentioned earlier, today I'm going to give a little bit of introduction. Hopefully it's not too boring or too technical about batteries, and why we are so keen to invest in them and work around them, and a little bit about battery manufacturing, how us as academics are supporting the industry, and what are the issues currently out there. And then we're going to have a look at the battery modeling, performance estimation, and control, and what sort of challenges are in there. And a good part of this talk today is about giving an idea of what sort of resources in terms of the data software we are using at the moment. So obviously, to give a little bit of motivation and to give you a little bit of introduction about where we are about that famous subject of transition to net zero. So in June 2019, there was the Climate Change Act that targeted that was passed, and it was committing to 100% reduction of greenhouse gas by 2050, and reduction to the level of the 1990, which is a quite huge commitment. And the government mentioned that the net zero means any emissions needs to be balanced by that time. And a big part of this is about bringing in the renewable energies and using them in different sectors. But as we know, this renewable energies always require energy storage because they are very unstable. And it's not just about bringing in the renewable energies, it's about distributing them, and it's about efficiently using them in different, let's say, household applications, electric vehicles, transportation systems, smart cities, etc. So in such a plan, energy storage system is having a very critical role, because that's how we're going to store this clean produced energy and then be able to use it. Looking at the applications, it's quite clear now that we need batteries. So initially the topic was quite focused around electric vehicles, but now there has been a shift from not shift, it's been having other areas included, such as micromobility systems. We're now talking electric aircraft and electric maritime systems. And so basically they are now everywhere compared to the compared to last 5 years. But the thing is that the cost of the demand is increasing, and as you see here, this is just given an indication that how much is going to change. It is predicted to change between 2020 to 2030. It's about 150 times growth, and it's huge. It's massive. The production costs, it's not very good at the moment, and it was actually quite interesting to notice that it was for the first time around 2020, exactly after the COVID situation, that the production costs started to go up again. So there was quite a good trend in production cost reduction. But then, because of obviously the situation that we all know what happened after the COVID and the recessions, etc., and the material access, the cost, it started to get higher and higher again, and the figures are actually at the same level with 2020 for 2030. What's the UK situation in this market, in this environment? Is according to the Faraday Institution's report, as I mentioned, Faraday Institution is the UK's maybe the key institution involved in battery research and energy storage research. As they have reported, UK to be able to keep up with that demand of the batteries and energy storage, needs to have 5 gigafactories of the size of 20 gigawatt hours by 2030, and 10 of them by 2040. So I just remind you that there's been just recently news about some battery manufacturers in the UK, such as Agratas, which is owned by Tata, sister company to JLR, and also another one in around Somerset. So these are not yet established. They are establishing, but they're not yet up and running.
You gotta understand the amount of motherfuckers that said it's a waste of fucking time. I'll never be able to do it. It's not a real fucking job. The amount of motherfuckers that never believed in me, bro. But God did.
Sorry, I
The
get a
amount of
noise.
motherfuckers tell you that you can't because they can't stop doing something. No, do not let anyone tell you shit.
Sorry, I get a noise on the presentation. Okay, that's all right. Okay, so the situation is something like this, and even if UK is quite successful in addressing those demands, it's going to just hold only about 5% of the European market, and it's quite small compared to what Germany is, for example, having at the moment. So these all basically mean that we need to produce a lot of batteries. There is cost and carbon footprint involved, but we also need to be quick to be able to hit that target of 2040, 50. One of the things around this area is the questions about why lithium-ion batteries. So energy density and power density of some other material, you'll see there is quite difference in here. So it is basically an ideal material if you look at things all together: density, capacity, and voltage range. If you're not familiar with the fundamentals, just a little bit about that in here as well. So when you charge a battery, we have lithium ions moving from the positive electrode to the negative, and when you discharge, it's just the opposite thing. And then, so it is about the active material, lithium, moving in here. It doesn't matter what's the shape and the structure of the battery. It could be a cylindrical cell, a pouch cell, a coin cell, or a prismatic cell. The manufacturing process is almost the same, and the applications are still around having them such that they live longer, they are able to provide to be fast chargeable, and to have higher capacity or keep more charge in them. With this background, I'm just going to give you a little bit about battery manufacturing now, and then a little bit of the software in it, and then we'll move to the battery performance. Please feel free to have your questions in the chat box, or at the end of the session, we're going to anyway give some time for the Q&A. So, as I mentioned earlier, the batteries, regardless of their, let's say, the shape and coin being a coin, cylindrical, the manufacturing process is very much focused around their electrode manufacturing, because that's the most precious part, that is having the active material in it, and it's quite similar. So we basically manufacture electrodes, and then we stack them and put them into shape to form a battery for us. The battery manufacturing process is being something like this. These are just the key steps, starting from mixing, adding solvents, coating that mix on a foil, then we have the electrodes in here, compressing those electrodes, and then we move to cutting, stacking them, packaging electrolyte, injection, and then we move them for testing, and then they're ready. The process is very similar to baking a cake. So you mix the material, and then you coat them on your baking tray, and then you leave them to dry in the oven, and then you take it out, you cut it out, you stack them together. Probably you use something like a jam, which is like that. I would say that's the separator in the battery. And then if you soak it into like syrups or milk, then that's going to be your electrolyte. And that's basically the same that we do with the batteries. The thing is that in here, there are a lot of questions to be answered, and that is mostly around the number of the variables and parameters that need to be taken care of in such a process. When you start with formulation, you probably start with 3, 4, 5 different material, and there could be a few combinations in here. When you move to mixing, the mixing speed, the mixing temperature, and also the mixing time start to show up as a control factor. When you move to coating, that coating speed. When you move to drying, that temperature of the dryer. These are gonna all show up as control factors, and then we will be ending up with a huge number of combinations of those key factors that all of them are having an impact on the quality of the electrodes, the slurry, and finally the cell that has been made. It has been reported by some particular manufacturers that the scrap rates that is associated with discovering the optimal combination of this material is about 8% in the R&D, and we are talking about precious material. We're talking about nickel, cobalt, lithium that are quite expensive, costly, and controversial. Even their mining is quite controversial. So there is a high waste in here, and leave aside the time that we need to take to optimize this. So what we do. One of the solutions in here, and one of the enablers, is looking at modeling the process. And there are 2 different approaches we could use in here. One for the manufacturing process, and then later for performance control. For manufacturing process, actually for both of them, we could divide this to 2 different areas. Those that are quite traditional simulation and control approaches by high performance models, and quite, let's say, capable software that we now have access to. And the other area is a little bit newer, around using AI, machine learning, and deep learning. So some of these logos may be familiar for you if you're an engineer. If you're not, I'm just going to show you a few of the case studies around what we use them, how we use them, and then around AI and machine learning. So it's more around using data directly without any first principle knowledge, without any knowledge about the mechanistics of the model. And sometimes we combine these two together. So AI is about having any mechanisms for decision. Even a simple if-then rule can be an AI algorithm. And then we move to the machine learning side, which is the I would say statistical part of AI, and then it is about deep learning. Deep learning is about having layers of models, one after another, to deal with the a little bit more complex problems. And the goal in each of these two categories is to link those key factors with interest responses. Those interest responses could be capacity, lifetime, and performance of the cell. So the question in here that we're trying to answer is actually, could we possibly use these models so we could predict the performance of the battery that we make, and then the performance of the battery that we use in a future application, without testing them, without necessarily testing every single scenario or doing experiments for them? Could we predict this without getting our hands dirty? And obviously, I wouldn't ask the question if we couldn't. Yes, we can, obviously, and that's the role of modeling, and by any aspect, by software or AI-based type of modeling. So yes, we can predict that performance. We can predict that that actually characteristic of a cell. But how this works in terms of either to be an AI or to be any other type of modeling activities, it's about teaching and training our models. It's more about AI, this picture that I'm showing here. So it's when you try to teach something to the computer, to your algorithm, it's very similar when you try to teach something to a baby. So the baby doesn't know anything when they're born. They're not able to distinguish anything. They're not able to answer any questions. But how you teach them is about showing examples. So this is a cat. You show a cat and then you give the answer. This is a cat. And then you show a croissant and then saying that, giving the answer, this is a croissant. And then you give multiple examples. You give lots and lots of them, and you show them at different situations. And then obviously after a few years, when the kid is seeing enough, then if you show a cat that she's never seen before, she should be able to say, okay, that's a cat or that's a croissant, and distinguish between them. And that's exactly how we train our algorithms, especially in AI. But also I would say that's the same for any type of other modeling activities. So in here we have our computers, our models, and then we have, instead of obviously cats and croissants, we have our batteries with different characteristics, different specifications. And then in here we have our data scientists, modeling engineers, and they're looking at different aspects such as fast charging, like life prediction, and similar categorization of the batteries. This is helping us, using a model is helping us to reduce, I'm not going to say eliminate, to reduce the number of experiments. So every single cell that has been made need to go through a testing process, but the amount of the tests, how many tests, and for how long they should be tested is having a huge impact on the production cost. So as much as we can reduce the number of these, replacing those by the predictions of the models, then it's going to be much more easier and faster to have volume production. How something like this is happening? We get the data, we get those examples, those cats and croissant examples from the lab. We use those examples. These are obviously the data for our system. We use them to train some specific models, and then we use that models to generalize the algorithm that they have identified in the data to newer cases, to the cases they have never seen before, and that means the testing. And then we use that for reducing the amount of energy cost or the workforce. So and also carbon footprint because this is also associated with the reduced number of the experiments. But then we also use it to provide some recommendations for future runs, for improving the faults, for optimizing the situations, etc. The sort of data that we usually get could be quite diverse, and that's one of the challenges that need to be answered in a field like this. We could get very simple data in the form of Excel sheets, what we call tabular data. We could be getting what we call temporal data, data that are dependent to time. There is a time dependency element in them, and data that could be images, scanning the layers of the scanning the layers of the electrode, so that they give us the information about the distribution of the particles, the shape of the particles, and this is giving information, because if you are able to correlate the shape of the particles and the porosity in the microstructure with the capacity, then later you can use it for designing a better battery. So it's about them. But combining all of these data together, or what we call data fusion, is not an easy task. It's quite a challenge, and that affects the quality of the models that we try to develop for that prediction. The question in here is that how we get that data. That data, obviously, as I mentioned, those are example scenarios, and we need to be pretty careful that what sort of examples we are providing, because we're not able to run hundreds of experiments. That would be very costly, especially in an R&D line of something like battery, that the material change every day, the requirements change from application to application. So we're talking about having a limited number of experiments, but such that they can cover the space for us, so that they are representative of the future scenarios. And one of the software that we are actually using in here is for what we call the design expert, or Minitab. Probably Minitab is more familiar for many. Design expert is a little bit more customized version of just for the design of experiments. And by this task of design of experiments, we are able to work around what scenarios we should focus on, and it kind of helps us to understand that we have already covered the space of the variables with the minimum number of the experiments in the lab. But then the breakpoints and the ranges are decided such that you can still do discoveries in between the ranges and in between the breakpoints. In terms of machine learning models, what sort of machine learning models we're using? It's pretty diverse. Sometimes they're very simple, such as decision trees. I'm sorry that I cannot go into the detail of all of this, but I'm happy to answer a few questions later. Some of these are a little bit more complex, such as those that work with the images. For example, the convolutional neural networks, which is a particular type of neural networks, or those that are able to quantify the uncertainty of the model and the confidence level of the model in its predictions, such as Gaussian process models. So it depends on the data, the requirements, and also the resources that we have available. So we choose between different models, we train them, validate them, and then we use them for predictions. For example, for a mixing process, some of the key factors in here for a mixing process is, for example, the mixing speed, the solid to liquid ratio, and also, for example, the thickness that we get after the coating based on the viscosity of the mix. And what we do here is, for example, we build quite a well-known model that is called the random forest. Random forest is a collection of decision trees. Decision trees work by predicting and categorizing and classifying data based on each feature at each branch. And for example, in here, with these control factors and looking at these responses, we are able to classify the cells that are being made based on their mass load and porosity with quite good accuracy. This matrix is showing that up to how many % we have been able to capture the class correctly. So basically, it means that if you give a model like this, a different combination of these control factors, it's going to tell you what would be the range of the mass loading or porosity. And we are able to do some complex analysis, such as it would probably say to us that for a mixed, for a process like this, viscosity is a much more decisive factor, much more critical factor than, let's say, for example, solid to liquid ratio. So if you're going to focus on measuring something in a better accuracy, you better focus on this. So such critical analysis is also an output of AI and data-driven type of models. The reason that we focus on data-driven models for battery manufacturing is that unlike the next category that I'm going to go for, performance and modeling of the battery after it's been made, the battery manufacturing, because of the high number of the key factors and the difficulty of capturing those, let's say, mixing, coding, calendaring processes by analytical or first principle models, data-driven models seem to be a much more efficient approach. And that's why we focus on AI and machine learning for battery manufacturing more than, let's say, first principle models. They have their own merits, but it depends that if you are to decide the key factors that are something at a high level, such as we have about 600 of them in a manufacturing environment for batteries, then data-driven approaches could be quite sufficient. The next thing is about when we have batteries made, then it's time to take them to the application and then start using them. But we don't just want to have good batteries manufactured, but we want to take most out of what they have. And that's when it comes to the performance estimation, the state estimation, and control of the batteries. So one of the very particular applications that I'm sure many of us are familiar with is the electric vehicle. So what is electric vehicle? So obviously it's a vehicle that has a battery pack instead of a fuel tank in it. And so you shouldn't be surprised to hear that about 30% of the weight of the vehicle is coming from this pack. And also about the same ratio comes from its, let's say, the cost, or even more than that. Even I don't have the, I guess I don't have the figure here, but yeah. And about 50% of the CO2 emission is related to the production. So so consider the CO2 emission of producing an EV. We're not comparing with a combustion engine now, but 50% of the total CO2 is coming from the battery manufacturer, is coming from the manufacturing of the cell. So that means it is quite important in quite obviously quite important element in the EV already. But so it means that if you have a battery pack, you want to take most out of it in the safest way and for as long as we can. Because not sure if you've heard, but the battery pack in your electric vehicle is going to be considered outdated after losing only its 20% of capacity. So a battery pack that is still having 80% of its capacity is being considered outdated for an electric vehicle. It can be taken out and used in another application, but in an EV, it's just done. It has had its life in an EV. So the thing is that we want to make sure that we monitor batteries' state and we use them safely as much as we can. But then there is still something left in them for their second, what we call second life. Obviously, we're not able to do this all by experiments. We cannot leave the battery just for 8-10 years to see what is going to happen to them. We need the answers now. The insurance company, the automakers, they need the answer right now based on how you use the battery. You need to know that how much energy is left in your vehicle, so you know how when you should plug it in for charging. You should be able to know that how long is left from your battery pack. So when it's time to get a new battery pack in your vehicle or to sell your EV. But also there is safety concerns around here. We don't want to push our batteries, so batteries are being taken to their edge when it's quite hot in temperature, quite low in temperature. They can lose their capacity in particular conditions, but we don't want to put them in those situations every single time. So we use modeling techniques. We use models to give us the answer. And then we validate those models and then generalize those to other situations and much more general, much more different scenarios. There are different models that we could develop for a battery, and one of the very first models that we need to develop is a battery electrical model. Obviously, battery is an electrical element, and it needs to produce voltage, power based on the input current, and we need to understand how much power and voltage it is producing based on different use cases and different scenarios. Obviously, battery is an electrochemical element, and probably the most accurate way of representing that by a model is having an electrochemical model that is taking care of the number of the particles, the shape of the particles, the distribution of the particles, the thickness of the electrodes, and many more other factors. This could be a very accurate model, and people are and when I say people, obviously scientists are developing this and using this, especially at the design stage, when you want to discover material, when you want to understand the ratios between the material. Scientists develop this and try to use this. But then these are quite complex to be implemented in applications such as EVs. Your processor in the electric vehicle, it's a small computer and it's not able to solve a model like this that is probably having about 150 equations. So what's happening? We do some simplifications. We do a simpler version of model that is called single particle model, that is assuming some taking into account some approximations, such as we consider all the particles to have the same shape, and then we replace all the whole electrode with just a single particle. The number of equations in here could drop to like 15, so it is now much more affordable by a processor in an EV or smaller applications. But for many other applications, this is this is also not affordable computationally. So we go a little bit, let's say, into abstraction, and that comes to the equivalent circuit models. So having battery as an electric element, we map its response to the response of an electric circuit that has resistance and capacitance and voltage source in it. And this is pretty much the simplest, and even though it is quite simpler, of enough accuracy that we use in the battery industry. So how we do this and where we do this, there are different approaches that we could use. One is by MATLAB software. And MATLAB has two different, let's say, environments. One is for programming and coding and scripting, and the other one is called MATLAB Simulink. And MATLAB Simulink is about having block diagrams of different operators, different equations in it, so we can just connect the blocks all together and create a block diagram of the whole system. So for example, in here we have a model of a battery. So that equations of the equivalent circuit model that I showed in the previous slide is being implemented in here. And then we have a controller connected to our battery. This controller in the battery terminology is called the battery management system. And it helps to control the battery's performance. So for example, if we're talking battery temperature, this controller is able not only to monitor the temperature, because we have sensors for temperature in here already. It is able to provide commands, for example, to heat up battery, to cool battery down in particular situations. So it is able to control the temperature. That's the same for the charge level, to the voltage level, because you don't want to overcharge your battery or its voltage to hit the limits, because then that's the things are going to get a bit ugly in terms of safety. So you keep things into its advised margins. So this is one of the softwares that is quite popular for developing battery systems here, battery modeling, battery models in here. The next one in here is for multi-physics modeling development. As I mentioned earlier, we have an electrical aspects to the battery, because that's an electrical element is giving us power and voltage, but it is also an chemical element, and also obviously there is mechanics about it, there is physics about it. So this is a multi-physics domain, and when we are talking about something like heat generation and heat transfer and temperature, we're talking multi-physics. So for example, in here, if you look at the particle level, the heat distribution could be different at different regions. And when you stack the cells together to create a module or later a battery pack, then when you cool them down or heat them up, that distribution of the heat is never uniform. So you want to understand which cell is getting hotter, because that is going to age the cell. And then how to cool that down. If you have a cooling strategy, you can model that in here, and then you could do simulations. And if that works pretty well in the simulations, then let's move ahead and implement this and build this, and then put that in a vehicle and test this. So everything starts here, and that's the importance of having a model. When we have cell or module or pack level models, the next thing is to take them inside an system such as electric vehicle, e-motorcycle, and that's when we need to connect the dots between the battery pack, between the motor, between the behavior of the driver, and then the ambient conditions. What's the temperature in the ambient? What's the road like? And many more things. So that's the powertrain modeling aspect, and one of the softwares that I'm sure there are different softwares. This is what I've been using, and that's called MSIM, SimCenter, and it's about having access to having access to different environments, from power electronics around here, from battery storage. It can let you to customize your battery model, and then you can connect the driver with a particular behavior, and even you can model your acceleration braking system and the strategy in here. So it can directly show you what's the impact of particular environment and driver's behavior on the lifetime or the capacity loss of your battery pack. And we do all this by models, so that later we do some validation tests, and then it's ready to prove a concept or show the merits of a particular technology. So related to the models that I mentioned earlier, there's also, as I mentioned, a control aspect. So we not only monitor, but also we try to provide commands, and this could be in, again, different type of software, but MATLAB is quite I would say capable in this area, and it's about having different if and thens, or this is just a simple if and then map, but it could be another type of controller, such as AI controllers or adaptive controllers, different type of controllers that can be implemented in MATLAB, and then you will have that in that box of controller. When you monitor the temperature, how to control that, that's the algorithm, then you can implement that in MATLAB and other softwares. So when we have these models, obviously an aspect to it is that we need to validate those models. Obviously, those validation is going to be for particular scenarios. scenarios that have been decided quite carefully and are believed by the expert of the area to be representative of the real scenarios later. Obviously, we are not able to test for every single, let's say, charge and discharge profile, because each driver, for example, has its own style. We cannot capture all of them, but testing on a few, it is going to show that how accurate this could be in general. So one of the things that we need to do in here is to really run those algorithms at the cell level, at the module or pack level in the lab. You use computers, not only computers that we normally use as a PC for, let's say, quite accurate simulations, but also smaller processors that we call, for example, examples are like from the DS-Space company, Micro Autobots or Escalexio. These are what we call real-time simulators. These are a little bit closer to what is available inside the electric vehicle or a bike. These are quite these are giving us a little bit more, let's say, computational power, more realistic computational power for applications. So we test them, we connect them to their controllers, we test them in chambers. Sometimes we take them to the, for example, in the EBSA project that I was involved, it was taken to the motorcycle itself, and then the motorcycle was sent for the test. So it shows that how good these models could be and what's the opportunity in that. So this was obviously, I guess this is the probably the last one, the last slide, connecting the dots from where we are in battery technology, what are we doing around battery manufacturing, how we're using modeling and software there, and then how we're using software modeling in performance estimation, and what are the steps that we take. And obviously everything is changing quite fast in this environment, and probably there's going to be lots of software or techniques that you might be familiar with, but all of these are contributing massively to that net zero future, and there is a great commitment around that. It's not just about having obviously sustainability, it's about having future careers. So this sector is looking at providing careers for the next generation. So knowing about the softwares, the opportunities, the techniques, the skill sets that are required, I believe could be a very good motivation for someone that is at a stage that tries to decide where to go and what to do, and engineering is a possible choice for them. Thank you for listening. Before I close for questions, if you are interested to hear more about our projects in WMG, I would invite you to go to our battery group website. Our general WMG website has other disciplines as well. Feel free to roam around and drop me a message. Feel free to connect me on LinkedIn. If you want to know a little bit more deeper in technicals, I know there are colleagues here from battery background. If you want to know a little bit more, please have a look at the papers that we have published. There's been quite interesting observations at both performance and manufacturing area in here. And if you are a business and an SME, or you're thinking about having your own business in battery, so in WMG, as a part of transition to clean transportation system, we have an SME support group. We are quite closely working with the smaller businesses, the smaller companies that are trying, like startups, that are trying to find their way in this huge world. So please drop me a message or email me if you want to know more, and I'd be more than happy to discuss any of these with you in more detail. Thank you for listening, and I guess I'm ready to take questions.
Right, thank you, Mona. I see in the chat somebody's added a question already. Can you see that? Or do you want me to read it out?
I can see, yes, I can see one question. I can read that. That's fine, John. So it has, have the industry or academia obtained better methods to model battery with minimal data, but with higher accuracy? The model needs to predict failure point and impact of different key performance parameters on cycle life. If yes, can you list their test method? So this area is very, very active. So if you look at the papers that have been published like 2-3 years ago, and then compare them with the papers that have been published maybe this year, there has been quite a development in the amount of the data and the nature of the data that people use. So, for example, and it's going to happen, and it's going to continue to be this same as this in the next few years. So, just an example, previously people were using like 20-30% of the cycle life to predict the rest of it, but now there are people that are working on just looking at the first cycle and then predicting as much as they can. So there's a huge difference. So there's been a shift in the AI techniques and also how people approach the problem. I am not able to probably name the methods. Most of them don't have any names. But if you look at the most recent published work, industry is a little bit behind, but published academic works, you should be able to see some very recent developments that use minimum data, but that minimum doesn't always have a limit. You could always go fewer than that. It depends on the techniques and the variables you measure, etc. Hope that answers the question. Okay. Supplementary question, but how can they predict the knee point from just the... Okay, that's what I'm saying. So it depends how you approach the problem. So something like data augmentation and sometimes it is about accessing the data of different sources, different cells, and then having your data, looking at the data at another C rate. For example, I'm predicting at a particular C rate. It just it could be very different from case to case, but there are definitely methods that looking at reducing the number of the data to predict the response. I'm sorry, I don't have the link for the papers, but I can look into it, and if you like to drop me an email, we can discuss a little bit more, and I'm happy to share some few details around that. Judy is asking, can your models act as a digital twin, providing real-time updates from batteries actually in use and feeding back? Yes, actually, that's what is happening. So the terminology of the digital twin is quite broad, but when we are having a model that is able to soak in the interaction with the environment and other units, we normally call that a digital twin. And what is happening at the moment in battery management systems, it is actually real time. So in real time, you measure the temperature or the state of charge, and then you feed back that in real time to your controller. So it gives you gives the battery the inputs that it needs to have for that particular temperature, etc. This is already happening in real time. Battery management systems, the controllers that I showed in one of the slides, micro Autobox, those are lab versions, but yeah, this is happening already in real time. For battery management systems, it is happening in real time. For battery manufacturing, it's not happening yet, because the equipment that we use for battery manufacturing doesn't have the real-time control aspect to it yet. The technology is not yet there. So for battery manufacturing is not real time. I hope that answers the question. So Mihir is asking, for the energy storage systems, the battery life cycle projection is expected to be 20 to 25% for Indian RE projects. Your take on the current battery quality to operate for the project lifetime with lower C rate and temperature work. By the way, sorry, BYD and CATL provide 20 years of, yeah, that's right. So right now it depends on the battery technology. They start from 8 years of like lifetime for the battery, and then they can go up to, like, as you say in CTAL, claiming that it can provide 20 years. Yeah, this is so true. So I don't get the question. So sorry, I don't know if that's a question, but yeah, the lifetime could be dependent on the battery chemistry and also the technology. No one is knowing what CATL is doing, to be honest, and how they are claiming to have 20-25 years of lifetime. But yeah, that could be true. That could be fine. So I'm not sure what the question is in that one, but feel free to elaborate if you want to, Mihir.
Could I ask a quick question? You've got the battery in the car for 8 years or so. And then you take it out and you put it in someone's home for their solar power. How long after that could you reasonably expect it to last?
So there's not been quite a clear answer to it, but because it depends on how much you use it. But they say between 5 to 10 years, 5 to 10 more years.
Because they never tell you that when they're trying to sell you one.
Yeah, that's so true. Yeah. So the other thing is that that lifetime is quite dependent on where the battery pack is coming from. So those are the things that are quite there are not much transparency right now around them, but there's been EU regulations, and normally UK follows the same, around usage of second life batteries past actually last April. So it's been about a year, and those regulations are gonna clear things a little bit more. So how long you should be expecting your battery to last. Those are the information that you need to know when you purchase a second life cell. Absolutely.
So you'd reasonably expect it to work, but it would lose charge.
Yeah, over time. Yeah.
Okay, thanks.
That's all right. Rodrigo is asking, can the same mathematical, electrochemical, multi-physics modeling techniques be applied to the manufacturing of battery cells at lab, pilot line, and industrial production level? That's a very good question. This is the scale-up challenge. So the answer so there is not a clear answer now. Some of the processes are easy to scale up. So when you do a coating at a particular speed, the speed could be probably the same when you go from lab to pilot line and to industrial level. In WMG here, we have our pilot line and things that we test in here. Then the next level is UK big. So you've seen that some of those are quite scalable, but some of those aren't. So for example, when you start doing a mix at grams in the lab, and then you scale that up to tens of grams in the pilot line, things change. That mix is not anywhere close to what you have done. So going from grams to tens of grams change things massively. That's like when you cook for like 2 people, or when you cook for 20, they're never going to show up the same. So that's a question to be answered in future. There are techniques that people are looking at, something like transfer learning, from transferring the knowledge from one scale to another, one area to another. But there is yet more to it. There's more to come.
You obviously need to go from a balloon whisk to an ear.
Yeah,
Chef.
exactly.
To use the cooking analogy.
Absolutely.
So I see we have a sensible question.
I hope that answers the question.
Yeah,
So that's why we have research going on at different scales. So, for example, we have lab scale. We have, for example, calendering machine at the lab scale, which is like something at the size of a laptop. And then we have our pilot line in WMG. And then we have UK BIC at the mid scale. And then we have a volume manufacturer, which is, for example, Agritas. So it is quite important. So these are connected in a line. So you can start things. That's the scale up part that we do as a part of our research in WMG, to be honest. And that is a lot of questions to be answered there. There is another question. Pranav is asking, how is UK working on battery technology? China is already ahead in the cell technology, apart from lithium, sodium, and other chemistries are also coming up. Yes. Could you give some insights on sodium-ion and other future technologies? So lithium-ion is quite good in terms of energy density, but it has been very controversial because mining the metals related to that, like nickel, cobalt, etc., is quite controversial. And sodium is a little bit lower in energy density, but then you can access sodium anywhere. There is plenty resources about that. So I would say sodium-ion batteries have a huge share in the future of the energy storage environment, and they are safer, they are cheaper, but there is still a lot of questions to be answered around them, and some applications that need higher energy density, some that need higher power, such as sport cars, etc. Those are still going to be around lithium or a combination. But what is UK situation? UK is working around both chemistries, like lithium, sodium is going to be quite a part of the future manufacturing plans. And but yeah, we in terms of the having a market share compared to maybe China, that's a very tough question to answer, because I would say that's my view. Even for niche applications, obviously particular technologies that we have here in the UK, such as sport cars, high performance cars, or particular applications, there is still a need to quite let's say specific batteries, such as what we developing here. But are they going to be but in volume manufacturing for the cheaper electric vehicles, are they going to be cheaper than what is produced in China? I wouldn't know that until we have something out in the market, and Agritas is up and running in the next 2-3 years. So let's see and be optimistic.
Okay. Any more questions? Mona, you mentioned maritime.
Yes.
Was that a serious proposition to power ships all the way across the ocean with electric?
Yes. Yeah. At the moment, to be honest, it is more around smaller, let's say, systems, smaller marine systems. But there is an interest from the area, because decarbonization is about those huge sources like airplanes and ships. These are massive sources of emissions. So there is interest around them. But if I'm looking at the electric vehicle industry and also then electric aircraft, Maritime is a little bit is still behind. That's because of the costs that are involved. And for those we're talking about huge energy storage systems, that their safety, their controllability when they are offshore, it is still a question. There is still a lot to be done for them, but it's going to happen soon. There are already some projects going on here in WMG, and then I'm sure we're going to hear more about those larger scale ones later in the next few years.
Yeah.
Mihir is asking, as a battery modeler, how do you keep yourself updated with changing battery technologies? So as I would say, as an academic, I go through the recent published works, what other research groups are doing around the world. So I read papers, I go to conferences, because that's probably where you hear about the very first ideas, the very novel ideas that has not yet been developed massively, but you hear them the very first time. So those conferences, networking events, webinars that are a little bit more technical on the area. So there are regular webinars in this battery modeling field. I maybe attend those, and the best source, I would say, the published work from other groups and collaborations, just to be in the loop and see what other groups around the world are doing, so you're not left behind. Hope that answers the question.
Okay. Any more? Oh, yeah.
All right. That's all right. The last one. How accurately should we expect the current battery management system in terms of its SOC, SOH estimation accuracy? How long battery management system OEM test, considering the estimation, can go for TOS if the sensor accuracy or the ECM model isn't updated? So currently the SOC and SOH estimations are pretty accurate. SOC is accurate for more than 99% in some claims, even more than that in some published papers. So there are methods claiming that it could be higher than 99 plus % accuracy. SOH estimation is a little bit below, because it's much more difficult to be estimated. But there is quite good accuracy around that as well. And it depends on the application. If there is a stationary application, then the SOH estimation could be much more accurate than an electric vehicle. So it really depends. But the level of accuracy is currently quite satisfying. But there is never an end to it. You want to know really with different environment conditions, with different use cases, the model that you have already is not covering all the scenarios. So there is always some uncertainty around that. And how the inaccuracy and not updating the models can affect the performance of the battery management. It can hugely affect if you don't update, and if you don't have an adaptive and updatable model, then after a few, maybe even months, when the state of health of the battery changes, when the ambient condition changes, when the temperature, when the season change, and you haven't updated the model, you're going to lose the accuracy. So it's quite important to have an adaptive algorithm for the model, especially for quite popular applications such as electric vehicles. In electric vehicles, if one is using an ECM model, they are updating the parameters once in a while based on particular techniques. You can probably, if you do a little bit of search in Google Scholar with the adaptive battery management systems, you should be able to read about it a bit more.